Lesson 6, Residuals. So before you watch this video and do this note sheet, you should do two other things. You should do the digital note worksheet. I'll show you that one. The line of best fit digital worksheet. It's one of the assignments. And then you should also do this Desmos problem set. The lesson number 6, Residuals. So if you haven't done that yet, stop the video, go do those, and then come back. So let's see here. Pull this up for us. So here we have an example. It's the same problem from the digital worksheet that you did, the ice cream cone. The weight of the ice cream cone sold in pounds is here, the X column. And then the average temperature on the day that many pounds of ice cream was sold here is the Y. So these two columns are the same as the XY chart in the digital worksheet that you did, where you used Desmos to make a graph. Now we're going to learn about residuals, and you also should have already done that Desmos problem set that I just talked about, the lesson number 6, Residuals. In that lesson, we saw that, let's see here, let me go back, let's go to that, let's take a look at that lesson. So you've done this lesson, and we learned a little bit about residuals, what they are. And if we skip through to, let's see, what is the screen? Say this screen right here, we saw that, or maybe the screen before, the line of best fit, none of the actual points are on that line. They are all a little bit off of the line. And if I click on one of the points, like that one right there, then it will graph on this graph on the right what's called its residual. Basically, it's graphing how far away that point is from what we're expecting it would be based on our line of best fit. So I can click on each point. Each of those now, these points that I'm clicking right here, are a little bit higher. They are more than what we were expecting from our line of best fit. And then the ones that fall below the line, such as that one and that one, those have what are called negative residuals. They are below where we would expect. They're below the line of best fit. So their residuals are negative. So going back to our note sheet, now we're going to record that information on our note sheet, or we're going to see how that's calculated. So how you calculate the residual is you find out what is predicted by the line of best fit. So for this ice cream situation, when you did that digital worksheet, this should have been the equation that you got. The slope is 0.78 with a y-intercept of negative 9.4. So what we're going to do is we're going to plug in the x value and see what the predicted y value would be. This was the actual y value. The average temperature was 6 degrees Celsius. We're going to see what is predicted by this line of best fit. So let's plug that in. Y equals 0.78 times 20 minus 9.4. And you can plug that into your calculator. And I'm going to look at my answer key. Here we go. I get y equals 6.2. So pretty close to the actual value, but not exactly. So to find the residual, we're going to subtract the actual, or the observed, which is 6, and we're going to subtract the predicted from our line of best fit, 6.2. And I get negative 0.2. So for that point, we have a negative residual. The actual temperature is a little bit lower than what we would have predicted from our line of best fit. So then we come down here. This is actually already calculated for you here. The x value is plugged into that equation, and here is the predicted y value. The actual y value is 4.5, so we're going to say 4.5 minus 4.64, and we get negative 0.14. another negative residual, so my actual value came in a little below what was predicted. These ones are done for us here. Let's go down here and do this one now. So we're going to figure out what is the predicted Y value when X, the weight of ice cream sold, is 19.5 pounds. So we're going to say 0.78 times 19.5 minus 9.4. Plug that into our calculator and you will get 5.81. So we will take our observed 6.5, this number, degrees Celsius, and subtract our predicted temperature, 5.81, and we get a positive 0.69. So this is a positive residual. So our point came in above what we predicted. We can actually see these points here on the line in our graph. 19.5, that would have been here. That's this point. See that it's above our line of best fit. And then this one here, the 18, 16, 17, 18. There's actually, it looks like two values for 18. This particular value for 18 is below, it's a negative residual, so that would be correspond to that point. Now we can actually graph the residuals themselves, and that's what you did in that Desmos assignment. It digitally graphed those for you. We'll take a peek back at that here for a second. That's what the second graph here on the right is the graph of these residuals, the difference between what was predicted and what was observed. So we can graph, on here we're going to graph these residuals. So we're going to take these points when X was 20, the pounds of ice cream was 20. The residual, the difference between the observed and the predicted temperature, was negative 0.2. So I'm going to put a little point down here, just a little bit below 0. When X was 18, it was negative 0.14, so a little closer to 0. We'll graph that residual. So you're going to graph all these residuals. I will do one more for you. That is 0.69. Let's see here. 19.5, 0.69, that I'm going to say that's about there. So you can graph all those residuals. Let's go to Desmos and see what that graph actually looks like. If I have that graph. There we are. I believe this is our ice cream data. So I can take those off. So here's just my line of best fit. Those green dots are our data points from our chart. And if I click this thing, this E, those are my residuals for each one. And that should match. Does that match what we calculated on our sheet? Yes, a little more exact, a few more decimal points. So these green dots here, I can actually take away my line of best fit dots. These green dots here on the x-axis, that's the graph of our residuals. And they're pretty close to 0. They're not really high or low. So that's a pretty good line of best fit when they're close to 0 like that. So let's do another one. Then this was the other problem from our digital Desmos worksheet, example 2, where we investigated the relationship between the amount of food waste measured in pounds and the number of people in a household. And you did that on that Desmos worksheet. And notice here, the data is not as linear as the other data, right? It's not falling in as neat of a line as what we have here for our ice cream sales and how they predict the average temperature outside. The more ice cream is sold, the higher the temperature is. So here, we have a line, we were able to do a line of best fit, but notice our residuals, like say this point right here, was really far off of what was predicted. As was this point here, a negative residual, very far off what was predicted. And so you'll see these graphed here. This point, when we graph it as a residual, is way down here. This point graphed as a residual is way up here. Let's take a look at our Desmos graph for those points. I think it's this one. All right, here's the graph for food waste. So I can plot my residuals. I'm going to take away my line of best fit points. Am I even going to take away my line of best fit itself? There's the graph of the residuals. So that matches what we see here on our note sheet. And so now you're going to answer this question. The bigger the residuals, so here's an example with really big residuals, as opposed to this example here where our residuals were small. The bigger the residuals, the more or less linear the data. Think about that for a second. Fill in your answer. And if you said less, you are correct. So when you have really big residuals, observed values that are pretty far off what's expected by the line of best fit, that means your data's not as linear. All right,